In this lesson, we will learn about complex numbers and operations over complex numbers, graphing quadratic functions, and solving quadratic equations by completing square using quadratic formula, and then look at some real-life applications. Let's explore simplifying square roots. We can rewrite 9 as 3 squared and cancel the square root and square to get 3. Similarly, we can rewrite 4 as 2 squared and simplify it to 2. 1 can also be expressed as 1 squared, and the square root of 1 would simplify to 1. But what about square root of -1? What squared is -1? Mathematicians came up with the concept that I squared equals -1, so we could solve quadratic equations. So we can express square root of -1 as the square root of I squared and simplify it to just I. Now that we know square root of -1 equals I, we can simplify square root of -4 by rewriting it as square root of 4 times square root of -1 and simplifying each of them separately and express it as 2i. Similarly, square root of -9 can be expressed as square root of 9 times square root of -1, where we simplify each of them separately and express it as 3i. So a complex number is a number of the form a plus bi, where a and b are real numbers and I is square root of -1. We express the set of complex numbers using this set notation and read it as the set of all numbers of the form a plus bi such that a and b are real numbers and I is the square root of -1. A is the real part of the complex number and b is the imaginary part of the complex number. Now, if I squared equals -1, then what is I cubed? We can express I cubed as I squared times I. We know that I squared equals -1, so -1 times I simplifies to -I. We can use the same technique to simplify I to the fourth, where I to the fourth can be expressed as the product of I squareds that can be expressed as -1 times -1 and simplified to just 1. Similarly, I to the fifth can be simplified to I, and I to the sixth can be simplified to -1. Wait a second, is there a repeating pattern? It looks like I, -1, -I, and 1 keep repeating. So to identify any powers of I, we can divide the exponent by 4 and use the remainder to simplify it. 4 goes into 13 3 times, and subtracting we get 1 and we carry down the next digit. Then 4 goes into 19 4 times, and subtracting we get a remainder of 3. So I to the 139 is equivalent to I cubed, which simplifies to just -I. What about I to the 459 power? We divide the exponent by 4, and after performing the long division, we get a remainder of 1. So I to the 459 power is equivalent to just I to the first, which simplifies to just I. So we now can find powers of I. Now let's explore operations over complex numbers. Given two complex numbers, 2 plus 3i and 5 minus 2i, we can add two complex numbers. Since there is nothing special going on, we simply drop parentheses and add the real parts together and the imaginary parts together. Similarly, we can perform subtraction. We first distribute the negative sign into 5 minus 2i and then add the real parts together and add the imaginary parts together. Let's use these numbers to explore multiplication over complex numbers. We can FOIL when multiplying complex numbers. So we multiply the first, the outers, the inners, and the last, and then add the imaginary parts. Note that we know I squared equals -1, so we get 10 plus 11i plus 6. And adding the real parts, we get 16 plus 11i. We need some terminology before defining division over complex numbers. Conjugate of a complex number a plus bi is a minus bi. So conjugate of 5 minus 2i is 5 plus 2i. Conjugate of negative 2i is positive 2i. Conjugate of 2 plus 3i is 2 minus 3i. Conjugate of 3i is negative 3i. And conjugate of 5 is just 5. Something interesting will happen when we multiply a complex number by its conjugate. Following the complex number 5 minus 2i and its conjugate 5 plus 2i, we get 25 plus 10i minus 10i minus 4i squared. 10i and negative 10i cancel each other out, and we get 25 minus 4i squared. We know that I squared equals negative 1. So replacing I squared with negative 1 and simplifying, we get 29. Note that the product of a complex number and its conjugate results a real number. We can now explore division over complex numbers. To perform division of complex numbers, also known as rationalizing the denominator, we need to multiply both numerator and the denominator by the conjugate of the denominator. Then we FOIL each numerator and denominator and get this expression. We substitute negative 1 for I squared and then simplify both numerator and denominator. Note that we know the denominator would become a real number since we multiplied the denominator by its conjugate. Since a complex number is of the form a plus bi, we need to separate the fraction to rewrite the expression in the form of a plus bi, and we get 4 over 29 plus 19 over 29i. Quadratic functions or parabolic functions have 3 different forms. F of x equals a times x minus h squared plus k is called the vertex form. The point with coordinates h, k is called the vertex of the parabola. If a is positive, parabola opens up, and if a is negative, the parabola opens down. Let's look at this quadratic function. Since it is in vertex form, we can identify the vertex of the parabola. So the vertex is at 1, 1. And a is positive, so the parabola opens up. To find x-intercepts, we set y to 0. To solve for x, we first subtract 1 from both sides and then divide by 3. We can see that no real number squared will ever be negative, so there are no x-intercepts. We can also see that the vertex is at the point 1, 1 and the parabola opens up, which indicates that the parabola will not intersect the x-axis. To find y-intercept, we set x to 0. Simplifying it, we get 4, so the y-intercept is at 0, 4. Plotting the vertex, the y-intercept, and the reflection of the y-intercept into axis of symmetry, we can graph the parabola. Note that the vertical line going through the vertex is called the axis of symmetry to a parabolic function. Here is another quadratic function in vertex form. We can identify the vertex at the point negative 1, 2, and since a is negative, the parabola opens down. To find x-intercept, we set y to 0. We first subtract 2 from both sides and then divide by negative 2. Taking the square root of both sides, we get plus or minus 1. Subtracting 1 from both sides, we get 2 different x-intercepts, one at negative 2, 0 and another at 0, 0. To find y-intercept, we set x to 0. Simplifying it, we get the y-intercept at 0, 0. Note that since there can only be one y-intercept for each function, we already knew that the y-intercept would be at 0, 0 from our x-intercept. Putting these together, we can graph the parabola. Here is another form of a quadratic function. This is called the intercept form. As you can see from its name, we can identify the x-intercepts from this form. C1 and C2 are x values of the x-intercept coordinates. Again, if a is positive, parabola opens up, and if a is negative, parabola opens down. You may have seen this before. One way to solve a quadratic equation is by factoring. Factors of negative 15 that add up to positive 2 are negative 3 and positive 5. The multiplication of two objects is 0 only if one or both of them are 0. So we set each factor equal to 0 and then solve each of them separately. Another form of a quadratic function is f of x equals ax squared plus bx plus c. This form is called the standard form. This formula can be used to find the vertex. However, we will use a different technique to transform the standard form into the vertex form to extract information and sketch the graph of the parabola. Again, if a is positive, parabola opens up, and if a is negative, parabola opens down. We can use completing square to transform a quadratic function from the standard form to the vertex form. To complete the square, we need to make sure the leading coefficient becomes 1. So we factor out 3. We also don't want a constant in the parentheses. So we leave -1 outside of parentheses on its own. We then take half of b, the middle number, and square it. Then we take b over 2 squared and add it to the set of parentheses. We have now added something to the expression and have changed its value. So we need to balance it out. It seems like we have added a 4, however, there is a 3 outside parentheses that affects 4. So technically, we have added 3 times 4 to the expression and need to subtract 3 times 4 from the expression to balance it out. We've now completed the square and have transformed the quadratic function from the standard form to the vertex form. We can use completing square in solving quadratic equations too. We first need to ensure we don't have a constant and the leading coefficient inside parentheses is 1. So we subtract 1 from both sides and factor out a 2. Then we take half of b, then square it, and then add this number to the expression inside parentheses. Technically, we've added 2 times 9 on the left side of the equation and need to make sure we do the same to the other side to balance it out. So we add 2 times 9 to the other side. After simplifying the equation, we divide both sides by 2 and then take the square root of both sides. Since we took square root of both sides, we give one side plus or minus, and then subtract 3 from both sides. We can also use quadratic formula in solving a quadratic equation. For any quadratic equation in the standard form, x equals the quantity of -b plus or minus the square root of b squared minus 4ac, all divided by 2a. So we can use the quadratic formula to solve the equation 3x squared plus 2x plus 1 equal to 0. We can see that a equals 3, b equals 2, and c equals 1. And substituting all of these values into the formula and simplifying it, we get -2 plus or minus the square root of -8 over 6. Since we have a square root of a negative number, we know that this equation has no real solutions. However, it does have imaginary solutions. We rewrite the square root of -8 as square root of 8 times square root of -1 and simplify it. Note that because these solutions are imaginary numbers, we need to separate the fraction and express the answers as complex numbers in the form of a plus bi. Let's look at this application problem. A ball is thrown from an initial height of 2 meters with an initial upward velocity of 25 meters per second. The ball's height, h in meters, after t seconds is given by h of t equals 2 plus 25t minus 5t squared. We're asked to find all values of t for which the ball's height is 12 meters. That means h of t equals 12. So we substitute 12 for h of t and try to solve the equation for t. First, we set the equation equal to 0 by subtracting 12 from both sides. Then we can factor out a -5. Unfortunately, this quadratic expression is not factorable, so we must solve for t by using the completing square technique or by using quadratic formula. Using the quadratic formula and simplifying it, we get 5 plus or minus square root of 17 over 2. And using a calculator, we can approximate the values of t. So the ball's height is 12 meters at around 0.44 seconds and 4.56 seconds. The next question is, at what time will the ball reach the maximum height? And what is the maximum height? The maximum height will be at the vertex of the parabola. So we'll need to find the vertex of the parabola. We can either complete the square and then find the vertex, or we can use the vertex formula. Using the vertex formula, we can find the x-coordinate of the vertex, which is 2.5. And evaluating the h of t at t equals 2.5, we get 33.25. So the ball will reach a maximum height of 33.25 meters at 2.5 seconds.